Okay, so this slide is about the supplementary for the electromagnetic wave. So this is the outline, and first I will let you know what is so-called the Maxwell equation in free space. So last time in the last chapter I let you know what is the Maxwell equation in differential form. So yeah, we can make some simplification to make it in free space. Okay, just later on I let you know what are the two conditions. Okay, and based on the Maxwell equation in free space, we can derive the wave equation. And based on solving the wave equation, we will get the solution, which is the EM wave propagate in vacuum. Okay, so first is the Maxwell equation in free space. So for the normal Maxwell equation, just say for the Gauss, the first one is the Gauss law. On the right side, we should have the term rho over epsilon naught. So rho is the charge density in the space divided by the permittivity constant. So so originally it's not zero, but in free space means we don't have any charge. So we just make it zero. And for the second one, Gauss law for magnetism, we don't have anything on the right side. So we doesn't need to change it. For the Faraday's law, we don't have any sources. So we still need to keep this. Term for the Faraday's law. But for the Ampere's law, originally this is J, or in the integration form, it should be like integration of B dot ds is mu naught I enclosed, and then if you just don't care about the displacement current, or maybe you can just write, this is the displacement current, this is the original current, which you should know it in chapter 29. So originally for the integration form, it should be the current on the right side, but for the differential form, it changed to be the current density. But here we also assume that it is zero, so there is no current or no charges to inferior the propagation of EM wave. So these are the two conditions. For the free space. Two conditions. So the first one, no charges. So which is to say rho equals zero. The second condition is of no current. So you can write it as J equals zero. So we don't have any charges or current to interfere the E field, the propagation of E field and B field. So it's called free space. If there are some current, then it will generate some B field. So to make the B field in the space different. Okay, so these are the two conditions for this free space. No charges, no current. Okay, free space, rho equals zero, J equals zero. Okay, so in this case, these are the Maxwell equation in free space, two Gauss law, Faraday's law, and Ampere's law. And based on this Maxwell equation in free space, we can derive the wave equation for the E field and B field. Okay, and in the derivation, we need a quantity or identity called curl of curl identity. You can just check it on Wikipedia. You can actually check it on Wikipedia. So the identity is like the F, as we have mentioned before, it is a vector field. Just as what I introduced, what is divergence or curl. So this is a arbitrary vector field, so it may be E field, B field, or any other vector field. Okay, so on the left side we have curl of this F, and then we take the curl again, because taking the curl of a vector space, it is still a vector space, and then you can take curl again. So you take curl of a vector field 2 times, which is equal to, the right side is a bit more complicated. This is, so yeah, in the parenthesis, this is divergence. This is divergence. So taking the divergence of f, it becomes a scalar field. Then you can take the gradient. Gradient, you can take gradient to a scalar field, just like in chapter 22, chapter 24, we have E equals negative gradient of V. V is a scalar field. V is a scalar field. You take the scalar field, just like how it changes in different direction, then you get the E field. Of course, you need to take the negative side. Okay, so this is a scalar field, you can take the gradient. And then minus, okay, this is a upside down triangle, and then square. Okay, what is this? This is called Laplacian. Laplacian. Okay, what is Laplacian? Laplacian is yeah, you can take Laplacian to a vector field, so which is actually the same as this upside down triangle and dotted with itself. So in Cartesian coordinate, if you still remember, this gradient in Cartesian coordinate is partial x, and then I hat plus partial y, and then j hat plus partial z, k hat. Okay, if you have gradient dotted with gradient, yeah, like this, so you will have this one dotted with itself, so you have totally line terms, I dotted with I dotted with j, I dotted with k, and then j dotted with I, j dotted with j, j dotted with k. So we all together will have 9 terms, but 6 of them will be 0. So the only term remain are this one dotted with itself. So I dot I will be 1. So we will have second partial derivative of x, and then plus the second term dotted with itself, second derivative with respect to y, and then second derivative with respect to z. Okay, so this is a scalar operator. Okay, we can usually call this one an operator. But this operator is a vector operator because yeah, it can operate to a scalar field and then make it a vector. But the Laplacian is a scalar operator. It can operate to a vector field and then it still be a vector field, because yeah, when you just look at this Laplacian, yeah, we don't have any vector there. Okay, you just take fx, fy, fz independently, and then in Cartesian coordinate, of course. Okay, so you might ask why this is correct. Okay, so if you don't, yeah, actually try to believe it. This is not a math class, so you can try to believe it is true. Yeah, but if you don't believe, you can try to verify by yourself. The calculation is not so difficult. Okay, so just like yeah, the only thing you need to do is to remember, this gradient operator is this one, and then you can calculate the cross product and then calculate the curl for 2 times. Okay, so you get the expression what it should be. Of course, you still have f is actually fx I hat plus fy j hat plus fz k hat. Okay, so you plug in this one and this one to there, and then you calculate the curl for 2 times. You will get some expression, and then you can also calculate this one. This one is very easy because yeah, this is only like this. Okay, so you just take the gradient operator. So it's just like you take partial derivative. You take the partial derivative to different component. And then you also try to calculate the divergence and then take the gradient. Okay, so finally you will find out both sides are equal, then you can verify this identity to be true. Okay, so here we will make use of this identity to derive the wave equation. Okay, so first of all we have this curl identity, and then first we will try to derive the wave equation for the E field. Okay, so we will need to make use of this one. This one is the Faraday's law. This is the Ampere's law, but in free space. So we don't have mu naught J here. Because J is 0. And then we also have divergence of E to be 0. Yeah, these two are all due to the free space condition, which means that rho is 0. J vector is also 0. Okay, so we have these two equations like this. Okay, so because we would like to find the wave equation for E field, so let's try to take the curl for this one on both sides. So we take curl for this one. Okay, so you can see on the left side we will have curl of E and then take the curl of E again. So we have this one. And then on the right side we also take curl of this thing. Okay, so negative, you can put it outside. So we have negative side. We also try to put this one inside the partial derivative of t. Yeah, so for most of the case, changing the order of derivative won't change the final result. Usually correct for engineering problem or physics problem. So but for mathematics, they may consider, you need to show changing the order of a derivative is okay. So, but we don't go too deep there. So we just assume that changing the order of derivative is okay. So we just put this one inside the partial derivative of t. Okay, so we have curl of b inside this partial t. Okay, so here we can see here is a curl of b, so we can make use of the second equation, which means that we can just plug in this one to here. And on the left side, because it is actually the left side of curl identity, so we can just change the left side to be this one. Of course, we need to change f to e. Okay, so we have a curl of e equals gradient of divergence of e minus Laplacian of e. Okay, the left side is like this. Just put this one into here, and then we put this one to here. So on the right side, we still have negative sign, and then here we have mu naught epsilon naught put in the front, and then we have partial t inside here. So we altogether have second derivative of e with respect to t. Okay, so on the right side look like this. Okay, so next we will make use of the Gauss law. The Gauss law, divergence of E is 0. So this one is nothing but 0. Gradient of 0 is of course 0. So finally this one turns out to be 0. So the remaining thing is this term equal to this term. So we just multiply -1 on both sides. So finally we have a Laplacian of E equals mu naught epsilon naught second partial derivative to E with respect to time. Okay, so this is the wave equation for the E field, and then we can also derive the wave equation for the B field with similar procedure, but the order slightly different. We still need to use this is Ampere's law in free space. This is Faraday's law. This is Gauss' law for magnetism. Yeah. And here we would like to get this term, so you can consider that. Yeah, we need to take curl for the Ampere's law rather than the Faraday's law. So we take curl for this equation. So on the left side we have curl of B, curl of B, curl of B. Okay, so on the left side is like this. On the right side, similarly, we just put this one inside the partial derivative of time. So we have a mu naught epsilon naught, and then partial t, and then we also have a curl of E put in here. Okay, so on the left side, which is actually the same as the left hand side of the curl identity. So here we can just put this one. We can just put this one into here. Okay. The only thing we need to do is change F vector to B vector. So on the left side we have a gradient of a divergence of B minus Laplacian of B, and then equals mu naught epsilon naught, and then mu naught epsilon naught. Okay, so here on the right side we can see this is a curl of E. This is curl of E. So we can make use of Faraday's law, and then we can just plug in this one to here. So here we have a negative sign. So we have a negative sign. This is mu naught epsilon naught putting here, and then here we still have this partial B partial t putting into here. So we altogether have second derivative with respect to time. So on the right side it looks like this. And then similarly, this one we can use the Gauss law for magnetic field. So this one turns out to be 0, and then we also multiply -1 on both sides. So finally we have a Laplacian of B equals mu naught epsilon naught second derivative of B with respect to time. So this is the wave equation of B field. So just you can see this is the wave equation for E field, and then the wave equation for B field. The whole equation are the same. The only thing is here we have E, and then here we have B, and then we can also see this term mu naught epsilon naught. Okay. So here we have two wave equation, each one of them for E field, one of them for B field. And then by solving this one, it will tell you that the speed of the light, of course it is the EM wave, and the speed of this wave is called the speed of light, will be c. Yeah, because in around chapter, I'm not sure, chapter 17 or 18, around that, of this textbook, it talks about the wave, not for the EM wave, but for the other mechanic wave, like the sound or whatever wave. So at that time, the wave equation will be like Laplacian of something, of the wave will be like 1 over v squared, and then partial, something like this, will be something like this. So on the right side, it is 1 over the speed of the wave square. So in this case, it should be something like the EM wave, the speed of light. So this one should be like gradient Laplacian of E. Laplacian of E should be something like 1 over c squared, and then partial E partial t. Okay, so by equating 1 over c squared to mu naught epsilon naught, we will get c equals to 1 over square root of mu naught epsilon naught, which is the speed of light. Okay, so yeah. So here we have already derived the wave equation, and here we would also try to solve the wave equation to get the solution. But of course, this Laplacian is like in three dimension, and in the textbook during the previous slides we mentioned a term called plane wave. If you still remember, it's just we just assume that we have an antenna, it will generate an EM wave. But if you are far away enough, this, of course, the wavefront will be the concentric sphere. But if this R is far away enough, then we will approximate the wavefront to be a plane, and then we call it plane wave. So if we choose the axis, which is the same as the propagation direction, then we just need to consider E field just in terms of one variable, let's say x. We don't need to care about, of course, in general, this gradient of E should be like a partial, second partial derivative of E, and then partial x squared, and then in x direction, and then plus second derivative of E partial y in, we will have quite a lot of term there. But here we just only need to consider, we only have one term because the E field only related to x, and it only propagate in x direction. So we only have this single term on the left side. Otherwise, if we don't choose a proper axis, then it might be quite complicated. But for simplicity, we just choose E is only a function of x, which means that it is propagating in the x-axis. Of course, it can propagate in other axes like y-axis, z-axis. Just need to change x to y or z. But here, if we just assume that E is a function of x, then the solution will only related to x and t. Okay, so here we try to simplify in one direction, the Laplacian in one dimension, which is the second derivative of E. The second derivative of E with respect to x. Okay, equals, on the right side it is still the same. Okay, so we will try to solve this one, which is not that difficult. Here we will use a technique for solving partial differential equation called the separable of variables, 变数分离. Okay, you may ask why we need to do this. The reason is it might work for some simple partial differential equation. So when you really need to solve some partial differential equation, you try this first. If it works, then it works. If it don't work, then you need to seek for other method. But it is the simplest one. So try this first. Because for solving partial differential equation, usually it is not so easy. So just try some simple method first, and then if it works, then you will be very happy. Okay, so the idea is that here we know E is a function of x and t. Okay, so of course it may be something like coupling together. Okay, just like suppose for a function x and t, it can be coupled together like let's say cosine of xt, then it might be coupled together. You cannot separate to something. Then it might not work. It may not work if you use the separable of variables. Here we will try to assume that e of xt can be separated into a function of x multiplied by a function of time. If this is true, then this method might work. But before you try to solve the partial differential equation, you don't know whether the solution will have this form. The function of x and function of time are independently. You don't know yet, so you can try. You assume the solution is having this form. Then you try to plug in this one back to the original function, partial differential equation, and then you try to see whether you can find a solution. If it works, then the step will be very, very short. Okay, so here we try to assume e of x comma t equals a function of x multiplied by a function of time. Okay, then we just plug in this one into here because we try to solve this partial differential equation. Okay, so here I just highlight e of x in blue color and then e of t in green color. So you can see on the left side, nothing special. I just plug in this one to here and here. So on the left side we have this one, on the right side we have 1 over c squared and then second partial derivative with respect to time, and then here we have ex times et. Okay, so the next step is as much as we take the partial derivative with respect to x on the left side, so e of t is independent to x, which means that e of t, we can put this term outside. So finally it turns out to be e of t. Otherwise, if it is like just say we have f of x times g of x, and then you take d dx, it doesn't really matter whether it is original derivative or partial derivative. If it is two function of x multiplied together, if you need to take the derivative, then it turns out to be the product rule, which is f prime of x times g of x plus f of x times g prime of x. Okay, so when you learn the calculus, you know we have the product rule. But here, as much as we can separate the variable, okay, one function of x and one function of t multiplied together. Okay, so here, this is a function only related to time, which is not related to x. So we can just put this one outside. On the right side, similarly, we only need to take the partial derivative with respect to time. So ex is independent to t, so we can also put this term outside. So the second row is like e of t times d ex dx2. Okay, so here, because this one is related to x and t, so we still write it as a partial derivative. But here, we already know this is only related to x. Okay, so we can write it as original derivative of first second derivative. On the right side, or similarly, we have a 1 over c squared and then ex putting outside. So only et inside, so we have an original derivative with respect to time for the et. Okay, so here you can see this is a green function multiplied by a blue function, and then this is of course a constant, and then multiplied by a blue function and then a green function. So we try to collect the green term and the blue term and the green term on the same side. So which means that we try to divide ex of x, et of t on both sides. So on the left side, et and et cancel each other. So on the left side we have 1 over ex, and then ex and then second derivative of with respect to x. So on the left side, it is only a function of x. It is not related to the time. And then on the right side, ex and ex cancel each other. So we have second derivative of et divided by et. Of course, we still have this 1 over c squared, just put it there. But this is the key point of separable of variable, which means that at the very beginning, we just try to assume the original solution is separable. And then finally, we also try to separable these two variables on two sides. In this case, this is a function of x. This is a function of x. This is a function of time. They equal to each other no matter which x value or which t value is. So you can just imagine, maybe we can just need to fix t to be a fixed value, let's say t0, and then we try to change x. Then they should still be the same, which means that this should be a constant. This should be a constant. Otherwise, if I try to change x to different value, then it cannot be equal to this function, which is only related to t. So we can clearly see that this should be a constant. And similarly, if I just try to fix x to be a value x0, then we try to change the value of t, then we can see this side should still be a constant function, which means that both sides should be a constant function. So we can just assume both sides to be a constant. Let's say it is a. We don't know what it is yet, but at least we know they are constant function. So that's the punchline for this separable variable. We try to assume the function to be separable, and then our goal is also try to make it separable. If it is separable, then we can assume they are constant function. Then we can move on. We can find a solution. If we are not able to separate the variable in the end, then this method doesn't work. Then you need to seek for other method to solve the PDE. Maybe you need to use something like a Fourier series expansion or whatever method. Okay, so yeah, so this is the punchline. We need to separate the variable on two sides. So each side only related to one variable. So in this case, it should be a constant function. And then we try to assume it to be a constant a. So which means that this one is equal to a, and this one is also equal to a. So we have two independent ordinary differential equation. We already convert this. This is one PDE, a single partial differential equation. We have already separated this PDE into two ODE. This is ordinary differential equation. Okay, so for ordinary differential equation, especially it is constant coefficient, then we may be able to solve it. So yeah, so actually the left side equal to a, and then the middle part also equal to a. Then we can try to move this term to the right side. Okay, we just move this term to the right side, move this term to the right side. Okay, so it becomes second derivative of ex equals to a times ex, and then second derivative of et equals to a times c squared times et. Okay, we have two independent ordinary differential equation. Okay, so similar to before, of course, a can be larger than 0, equal to 0, or smaller than 0. Okay, but similar to what we have learned in chapter 31, a is smaller than 0 will be most useful. Okay, so we can quickly see why. The first case is if a is larger than 0, then if a is larger than 0, then you can try to write out the characteristic equation. So the characteristic equation is like a second derivative, we change it to s squared. and then a is a positive value. This is the original function, so equals to a. Okay, this is the characteristic equation. And here a is larger than 0, which means that we can take the square root, which means that s is equal to plus or minus square root of a. This is a real value. Okay, real value means that the solution will be something like exponential to square root of ax, and then exponential to negative square root of ax for ex. Okay, so and similarly, these two are quite similar. The only difference is that we have c squared here. So in this case, s squared equals to ac squared, which means that s is equal to plus or minus square root of a times c. Okay, so the only difference is that here we have c. Of course, this is a function of x, so we have x here. This is a function of time, so we have t here. Okay, so these are two homogeneous solutions. These are two homogeneous solutions for t, et. Okay, so in generally, we need to write out the general solution, which means that we need to have the linear combination, which means that we multiply this one by a constant a, multiply this by another constant b, and then add them together. So this is the general ex. So this is the general ex of x. This is et of t. So similarly, we have a constant capital C. So yeah, try to distinguish this. Capital C is just an arbitrary constant. This C, later on you know this is actually, actually you already know this is the speed of light. The speed of light. So here we have capital C multiplied by this solution, multiplied by this one, and then plus D multiplied by this solution, and then together. So this is et of t. And of course, originally we assume that ex comma t is ex times et, which means that we just multiply these two functions together, which should be ext. But we actually don't like this solution, because if this one x tends to infinity, this one exponential will also go to infinity. So this is not so good, because as you know, the energy stored in the E field is like 1/2 epsilon naught E squared, or something like this. Something like this. So if E tends to infinity, which means that there should be infinite energy there, so which does not make sense. So we just try to regard this one. It's just like exponential decay, but it will exponentially grow in the other side. So this is not good. Similarly, if a is equal to 0, which means that the right side will be 0, which means that the second derivative of ex is just 0. So you integrate 2 times. Integrate 1 times, it becomes dx. Dx will be a constant. Let's say b, and then you integrate again. So it becomes ex equals b constant, and then become first order, and then add another constant. Okay, so a plus bx, c plus dt. Okay, this is not good either, because if x tends to infinity, then ex also tends to infinity, which is not good. So it will tends to infinity. Ex t will tends to infinity, which is not good either. So finally, it should only be the last case, which is a to be smaller than 0. If a is smaller than 0, we can try to define it to be a negative k squared, because k squared is larger than or equal to 0 for arbitrary real number of k. But of course here k is not 0 either. So k squared must be positive. So negative k squared must be negative. Okay, so here we assume that a to be negative. So k is not 0, k is not 0. And usually we will define k to be a positive value, even though negative square will still be positive, but here we also have k to be a positive value. Okay, so in this case, a to be negative k squared, which means that if we try to write out the characteristic equation, it becomes s squared equals a times 1 is a, but a is negative k squared, which means that s should be plus or minus jk. J is of course negative, square root of negative 1. And then similarly for the second one, s squared equals negative k squared c squared. So we have s to be plus or minus jkc. Okay, so here, of course, for the first one, which is for this ordinary differential equation, so jk, this is the imaginary part. But yeah, actually reach like we would assume that ex to be exponential to sx. X is the independent variable. So we originally should assume that ex to be exponential to sx, and here s to be plus or minus jk, which means that we should have oi, or you can write it as a plus or minus ik. Okay, so we have exponential to ikx, exponential to negative ikx. Okay, we have this one. And then for the et, yeah, originally we should write it as, the solution will be et to be exponential to st, and here s to be this one, which means that originally it should be like exponential to ikct, or plus or minus. Okay, here we write it as exponential to I omega t, which means that we also have omega to be kc. Yeah, actually in the textbook it tells you that k equals 2 pi over lambda. If you still remember. Okay, whether it's correct. So here omega equals kc, which means that k equals c over omega. Omega is the angular frequency, which means that it is like k equals omega over c. Okay, should be omega over c. Omega is the angular frequency, which means that it should be 2 pi f over c. And then if you still remember, c equals f lambda, which means that if I just move c to the right side, lambda to the left side, we have lambda to be 1 over lambda to be f over c. So here we have f over c, which means that it should be 2 pi over lambda, which means they are the same thing. Okay, so here we have omega equals kc, which is compatible to k equals 2 pi over lambda, or also this one. Okay, so here we have ex to be exponential to plus or minus ikx, and then e of t to be exponential to plus or minus I omega t. Of course, we should have something like a times this one plus b times this one added together, and then c times this one and d times this one, and then added together, and then we multiply them together. But yeah, actually we can just like something have just say we have a prime exponential to ikx, and then plus b prime exponential to negative ikx, and then times c prime times exponential to I omega t, plus d prime exponential to negative I omega t. something like that. And then we can just explain it. Okay, we have this term multiply. Yeah, just say we have this one multiplied by this one. So we have exponential to ikx plus I omega t. So I can factor out. So the first term will be actually this one. We have added and then added. So these two, we have a plus ikx and then plus I omega t. And then we have the second one to be ikx and then negative I omega t, okay, which is actually this one. Then we also have, let's say, green color, b exponent, this one, exponential to negative ikx, and then multiply by this one. Okay, this one multiplied by this one, which should be negative ikx, and then plus I omega t. Okay, negative, which is plus I omega t. Okay, so it is this one. And then finally, we also have this term multiplied by this term. Okay, so we have a negative ikx, negative I omega. So we have negative ikx, negative I omega t. Okay, so we all together have 4 terms. And then, yeah, of course, it is like a prime, c prime equals c whatsoever. But they are undetermined variable. So we can just make it a, b, c, d. And based on this thing, we know that if we have kx minus omega t, which means that the wave is propagating in positive x direction. If it is kx plus omega t, then these two waves are propagating in negative x direction. So usually in the textbook, it just tells you that, we just assume that it propagates in positive x direction. We should only have the first two terms. To make it like propagate in positive x direction. Okay, just hold on. This is a complex exponential, but actually the solution is like cosine kx minus omega t. At least we know we have a kx minus omega t, but yeah, this is a complex function. Why it would be like this? Yeah, the reason is that, yeah, in the real world, we have the EM wave should be in real number. It should be a real function. So here we should make some, we should have some condition that A is the complex conjugate of B. A is the complex conjugate of B. Then finally, the imaginary part will cancel each other. The imaginary part of these two will cancel each other. The only remaining stuff is like, it's actually this one. The reason is that if we have, originally it is like e of xt equals a exponential to I kx minus omega t, and then plus b exponential to negative I kx minus omega t. Okay, we just ignore the last two terms because we already assume that it is propagated in positive x direction. Okay, here we also have A to be complex conjugate of B, which means that A is like A plus JB, and then B is A minus JB, something like this. Okay, so here we have B to be complex conjugate of A, or A equals to complex conjugate of B. So here we have A exponential to I kx minus omega t, and plus A complex conjugate exponential to negative I kx minus omega t. Okay, so actually this is like A exponential to I kx minus omega t. and then plus. Okay, so this is like the whole thing a exponential to I kx minus omega t, and then whole thing take the complex conjugate, because yeah, this one is like, yeah, if you still remember cosine, exponential to I theta is cosine theta plus I sine theta, and then exponential to negative I theta is cosine theta minus I sine theta. Okay, so these two are complex conjugate to each other. This is the real part the same, and then the imaginary part have a negative sign. So they are complex conjugate to each other. And then if we just take out the complex conjugate, yeah, just take out the complex conjugate to the outside. So this thing and this thing are the same. And if a thing, we have a complex number or a complex function added with this complex conjugate, then finally it turns out to be real function, because just say here a and b are complex conjugate to each other. So if you just add them together, a and a will be 2 small a, and then jb and negative jb will cancel each other. It becomes real. So finally it remains the real part. For this one, the real part is like cosine of this one plus I sine this one. So finally it becomes em cosine of kx minus omega t. Okay, that's why this final solution will be like this. Of course, in the textbook it write it as a em times sine of kx minus omega t. So there is only a phase difference, which is not so important. So if you just don't care about the phase, cosine or sine doesn't really matter. But based on solving the wave equation, we can get the solution to be like this. Of course, you can still put the phase there. The reason is, if a is also a complex number, then a can be written as something like a can also be written as something like a to be em exponential to j phi. Then this phi will also go in here. So finally it becomes em cosine of kx minus omega t plus phi, something like this. Then you can have a phase there. So if a phase is like negative 90 degree, then cosine will change to sine. Okay, so if you can have arbitrary phase, then yeah, it is the most general case. The most general case will be like this: em times cosine of kx minus omega t plus phi. Okay, so yeah, if phi is negative 90 degree, and then it becomes this form. Okay, so let's explain why we get the EM wave to be like this. And similarly, we can try to solve B of x, which is like as much as we have this solution for E field, then we can try to take plug it into the this one is the Faraday's law. Okay, Faraday's law, which means that we take partial E partial x. Partial E partial x, okay, equals to negative partial B partial t. Okay, then we can just plug in this one into here. Okay, so which means that, or actually we put this negative sign to the left side first. So we have partial B partial t here, and then equals negative partial E partial x. And then we plug in this one into the right side. So yeah, so here we have em. First of all, we have em, and then cosine, take the derivative, become negative sign. So negative and this negative cancel each other. Okay, and then we have sine of kx minus omega t. And then for the argument of cosine, we need to take the chain rule. Okay, so we need to multiply it by this is partial x. We need to multiply by partial x kx minus omega t. Okay, so we have k in the front. This is the function of t, which is a constant to x. So yeah, this turns out to be 0. We only have kx and then partial x, which become k. So we have k sine of kx minus omega t. Okay, this is partial b partial t equals this one. So we can integrate on both sides with respect to t. So finally we get bxt to be, we integrate this side, sine will become negative cosine. Okay, just keep in mind, we have a negative sign in the front, and then kem negative in the front, and then sine become negative cosine. We still have cosine here. Then we need to divide the derivative of this thing, which is the chain rule or change of variable. So we need to derive t, and then kx minus omega t, or partial t, kx minus omega t. Okay, so kx is a function, is a constant to t, so we have 0 here. Okay, this one, negative omega t, partial t, so we should have negative omega. So this negative side cancel with the negative side from here. So finally we have a positive sign. And then we have omega in the denominator, due to this one. Okay, so finally we get this one. And and if you still remember, we just have k omega, or omega equals kc, So here we have omega equals kc. So we put it to here, or actually put it to here. So we have k over omega to be 1 over c. So we should have a k over omega equals to 1 over c, which means that this one is like em over c cosine kx minus omega t, and this is actually bm. So we get this em over bm equals to c. So that's why the em and bm, which is the amplitude of the E field and the B field in the em wave, should have a fixed ratio, which is the speed of light. Okay, so so in this case, we have the solution. This is for the one-dimensional wave equation. But originally, it should be a three-dimensional wave equation. If it is the three-dimensional plane wave, okay, so we just change x to be r vector, which is the direction of the propagation. And then here it becomes k hat. Okay, the wave number can also be a vector, can also be a 3 vector. So k dot r, which define the propagation direction. Okay, so we have a k dot r, and then minus omega t will still be the same. So this is for 3 dimension. Okay, so our vector is the wave propagation direction. Okay, so it's originally an animation, but if you are interested to see, you can just Google it. You can or Google it, or just find it on YouTube. You can easily find that. Okay, so finally, we also would like to explain why the Poynting vector has the definition like that. Okay, so here we also have, because the EM wave is a sinusoidal, if we just assume it is a single frequency with of course it can consist of a multiple frequency, but as much as all the things are linear, and especially for the wave equation or the Maxwell equation, the things are linear. So even though if there are multiple frequency within the space, then you can consider different frequency one by one. Then you add them together. Okay, so here, suppose every single frequency we have amplitude. So the root mean square value will be the amplitude divided by square root of 2 for both E field and B field. Okay, so and then UE is 1/2 epsilon naught E squared. If you still remember in chapter 25, when we talk about the capacitor, this is the unit. This is the energy per unit volume. The energy per unit volume UE. At that time, we just write it as U, or I'm not really sure whether we write as UE or U, but in order to distinguish the energy density stored in the E field and the B field, we use UE here, and then UB for the energy density stored in the B field, okay, which is B squared over 2 mu naught. Okay, so as I mentioned several times, so they are derivative. So for the E field version, you just need to change E to be B, and then epsilon naught to 1 over mu naught, epsilon naught to 1 over mu naught, and you will get the derivative equation. Okay, so here, if they are independent things, then UE should be like this, UB should be like that. But in the EM wave, as much as we have E to be CB or EM to be C times BM, so we don't really need to care about the subscript. As much as they are the same thing, it's okay. So suppose UE is 1/2 epsilon naught E squared, we can change it to CB. Okay, and then as much as it is squared, so we have C squared, B squared. And then for EM wave, C squared is, we know C equals to 1 over square root of mu naught epsilon naught. Okay, so C squared is 1 over mu naught epsilon naught. So we have mu naught epsilon naught here. And then epsilon naught and epsilon can cancel each other, which means that it turns out to be B squared over 2 mu naught, B squared over 2 mu naught, which is actually the same as the energy stored in the B field, which means that in the EM wave, the energy stored in the E field and the B field are the same. Or the energy density stored in the B field and E field are the same. Okay, so here we talk about this is energy per volume, which is so-called the energy density. So the total energy in the EM wave will be UE plus UB, which is 2 times of UE, because these two things in the EM wave are the same. So which is actually the same as 2 UE. Okay, so which is epsilon naught E squared. Okay, when we talk about the Poynting vector, which is about the energy per time per area, so you can try to consider, this is volume. So actually we need to link these two things together. So here we have epsilon naught E squared, and then so here we also have epsilon naught E squared, and then we still have C. So let's try to think out what is the meaning. So energy per time, energy per time, and then per area. This is volume. Area is 2 dimension. Volume is 3 dimension, which means that this thing you can consider it is energy per area. The the cross-section area, and then consider the length. Consider the length. So you need to multiply by the length in the denominator. Of course, you also need to multiply in the numerator so that they are equal to each other. And then you also have the time. You also have the time put in here. Okay, so this one, area times the length will be the volume. So this turns out to be volume. So this thing is actually energy per volume. So we have this epsilon naught E squared. And then the remaining thing, length per time is of course the velocity. Velocity, which is the speed of light. So we have c times epsilon naught E squared. Okay, so yeah, so how can we change this to there? Okay, so here c will be this thing, or let me see, or here we have e squared, and then we have e to be cb, so which means that e squared will be e times b times c. We also have a c in the front, so we have c squared epsilon naught, c squared epsilon naught eb. Okay, so c squared, c is 1 over square root of mu naught epsilon naught, which means that c squared is 1 over mu naught epsilon naught. Okay, so we change this one to be 1 over mu naught epsilon naught. So we multiply by epsilon naught eb. So epsilon naught and epsilon cancel each other. Finally, it becomes eb over mu naught. And then in the textbook, it just tells you that the Poynting vector s is actually e vector cross b vector over mu naught. So that's why the definition of Poynting vector is like that. Okay, so this is pretty much